Howdy Ags, welcome to our Biomedical Electronics supplemental video. Today we're hoping to explain some of the basics behind operational amplifiers, the principles on how they work, and give you an example of how to solve one if you run into it in a classroom setting. So if you look down to the bottom right of the screen, you can see an example of how an op-amp often looks on a circuit diagram. If you look at the left side of the op-amp, you can tell that there are two input voltages. The upper of these two voltages, V+, is known as the non-inverting input. If you look at the bottom of these two, signified by V-, is known as the inverting input. These two inputs are then sent through the op-amp and the difference is found between the two voltages. This voltage, after being multiplied by the gain, which is equal to AOL, is then sent out as a output voltage seen to the right as V out. So some common characteristics of operational amplifiers is that they have a very high input impedance and a very large open loop gain, which is AOL. AOL is often a very unreliable factor when using operational amplifiers, as the gain that is caused by the AOL is very unreliable and is very, very large, up to almost 1 million in some cases. So some principles of ideal operational amplifiers is that there are two main rules that we follow when it comes to operational amplifiers. The first rule is that no current flows into either input terminal. So no current flows into the terminal here or into the terminal here. And the other rule that we use is that there is no voltage difference between either input terminal. So the voltage here and the voltage here are equal. So the steps we use to solve an ideal operational amplifier is seen as followed. First, we begin by using nodal analysis to create the equations at the node of interest. So we begin by choosing our nodes, which may be here, here, or here. And in other examples, there will be often be more nodes that you have to solve at. From there, you create your nodal equations using Kirchhoff's current law, and then using the ideal op-amp rules to find the output voltage. So using the principles that the voltage here and the voltage here are equal, and using the idea that there's no current flowing into either one of these terminals, is what you're going to use to solve for the equation. And lastly, you're going to compare the output voltage here to the voltage source, which is often given to you in the problem, to see if the signal is saturated. As the voltage source supplies the voltage that creates the output voltage, the signal can easily become saturated if the V out is greater than the voltage source. So if V out is greater than Vs, then what you have to do is set V out equal to Vs. So we are going to give an example now.
We will now begin analyzing the inverting differential operation amp. First, we will label our nodes. This will be Vi for the inverting, and this will be V sub n for the non-inverting. We can now say that Vi is equal to Vn. Now we will begin nodal analysis. So starting at this first node, we will say that Vi minus V1 over R1 plus Vi minus V out. Because this node has no resistor or capacitor or anything that is impeding the voltage source, we will say that this node is also V out. This will be over resistor 3, which is all equal to 0. Now we'll begin node 2 by saying Vn minus 0, because it is connected to the ground, over R4 plus Vn minus the second voltage source over R2 is also equal to 0. Here we can start by analyzing this equation and solving for this Vn term. From now on, we will use Vn. So to begin, we will multiply this first term by R2 and the second term by R4 to equate the denominators. This will give us R2 times V sub n plus R4 all equal to 0. Now we will solve for this term here by pulling out like terms. So here we can say Vn times R2 plus R4 is equal to R4 times V2. We will divide this over, and our Vn will be R4 times V2 over R2 plus R4. Just like in the first part of solving this, we will use equation 1 and we will equate the denominators in the same way. This will give us R3 times Vn minus R3 times V1 plus R1 times Vn minus R1 times V out. All still equal to 0. We will solve for this Vn term. We will pull it out and have that multiplied by R3 plus R1 minus R3 times V1 and equal to R1 times V out. We will divide this whole term to get V out by itself, which will leave us with R3 times V1 minus V7 R1 plus R3 all over R1. We can further simplify by saying that this is equal to R3 over R1 times V1 minus R4 V2 over R4 plus R2 by plugging this term in for V7, R1 plus R3, all over R1. Finally, we'll simplify one last time. We'll pull out this R4 and put it over the R1, multiply by V2, here we have our final voltage equation. In many circumstances, you may find that R1 is equivalent to R2 and R3 can be equivalent to R4. This equation becomes V out is equal to R3 over R1 multiplied by the difference of the voltages. This will give you a clear equation for the gain